Hi friends, let's say I have two masses here. They are going to attract each other with a force, that is the gravitational force. Now let's say we have two magnets. Again, two magnets, they either attract or repel each other with a force called a magnetic force. But let's say you have two charges over here. Again, the two charges may attract or repel each other. Now what is this force known as? It's called the electrostatic force, and that's going to be the topic of this video. We are going to look at Coulomb's law, which gives the formula for electrostatic force and tells us what factors it depends on. I'm going to make the concept of electrostatic force and Coulomb's law absolutely easy for you. So guys, make sure you watch the video till the end. But before we begin, I just want to remind you, do check out the courses on our website manochaacademy.com and our Android app. All the links are given below. All right, let's dive into the world of Coulomb's law. There are two types of charges, positive and negative. Let's say we have two positively charged bodies like this. What will they do? That's right, they are going to repel each other. They are going to push each other away with a force. So both these positive charges are going to repel each other with a force. Now what if you have two negative charges? Once again, the two negative charges, they are going to push each other away. So they will also repel each other with a force. Now what if you have a positive charge and a negative charge? In this case, the two charges will attract each other. They will attract each other with a force. So guys, as you can see, we can summarize this that like charges, same type of charge, positive, positive, negative, negative, like charges, they repel each other. So we can say like charges repel each other. But if you have unlike charges, one positive, one negative, unlike charges attract each other. And you can see it's just like magnets, right? Like in magnets, you have North Pole, South Pole, unlike poles, they attract each other. And North Pole, like poles or South Pole, they will repel each other. So remember this, like charges repel each other, unlike charges, they attract each other. Now they're repelling and attracting with a force. What do you call this force? That's right, it's called an electrostatic force, the force between charges. So let's write that down. We are talking about the force here is it's called an electrostatic force. And that's what we are going to be studying in Coulomb's law, that what is this electrostatic force, how does it depend on these charges or the distance between the charges. So let's look at the famous Coulomb's law, which deals with the electrostatic force between two charges. So remember, Coulomb's law is for electrostatic forces. So as an example, let's say we have two charges here, Q1 and Q2. And let's take them both to be positively charged. We are positive people, right? So we are going to take both these charges, let's say they are positive. Now remember, like we learned that two positive charges, what's going to happen? They are going to repel each other because like charges repel each other. So they're going to push each other away with a force. So let's mark the force here. So these like charges will repel each other with a force. So should I mark the force like this? Should I mark the force like this away from the charges? But there is one mistake here, because Coulomb's law says that the force is not in any random direction. It is along the line joining the two charges. Okay. So because the two charges are positive, there's going to be a repulsive force, so it's going to be away, but it is along this line. So along the line joining the center of two charges, so I should draw the force in this direction. So this is one force, and there will be an equal and opposite force. You guys know from Newton's third law. So again in this direction, so continued off in this direction. So along that line, this is the other force. Okay. So these are the two electrostatic forces, and usually we label them like this, that this is the force on charge 1 due to 2. So we mark it as F12. Okay. Similarly, here I can mark F21, the force on charge 2 due to 1. And let's say these charges are separated by a distance r. Now, there's one more important point about Coulomb's law, that it is valid only for point charges. What do we mean by point charges? Very, very tiny in size. Okay, I'm not talking about the value of the charge. They're very small in size, like you put a dot on your paper, right, with a pen. So they're very tiny in size. So please remember, Coulomb's law is valid for point charges only. Very, very tiny in size. Okay. So the first thing Coulomb's law said, that the force will be along the line joining the centers. Now, what did he say about the magnitude of the force, the value of the force? What does it depend on? What factors does it depend on? So just like gravitational force, we are predicting here that it will depend on, like gravitational force used to depend on the masses. So here, similarly in Coulomb's law, it depends on the value of the charge. So obviously, if this charge is more, the force will be more. Similarly, if this charge is more, the force will be more, right? You guys agree? So we can say that the magnitude of the force, right? The magnitude of the force is directly proportional to Q1, okay? And it is also directly proportional to Q2. So I can combine the two and say it is directly proportional to the product of the two charges, right? Q1 times Q2. So both are combined here, okay? And what about the distance? What do you guys think? So if we increase the distance, will the force increase or decrease? So intuitively, you're getting a feel that as you move the two charges further away, the force will weaken. The closer you bring them, the force is strong. Okay. So it is clearly, with the distance increase, the force is more, right? Oh, sorry, with the distance increase, the force is less, and vice versa. But Coulomb said that it just doesn't depend on the distance. The force is inversely proportional to the square of the distance. And that is why we call this the inverse square law, just like gravitational field. So think it just like gravitation, right? The gravitational force, it is inversely proportional to the r square. Okay. So is this clear? Here we are talking about the magnitude of the force. So you guys know these two forces are equal in magnitude, but in opposite direction. So we can say F12 is minus F21, but their magnitude is the same, right? So, and minus we write because they are opposite in direction, okay? Now, when you have these two proportionalities, what do? So typically the thing we do is we combine them. So that's what we are going to do here. We are going to say force is directly proportional to Q1, Q2, the product of the charges, by r squared. Make sense? Okay. And now, when we want to change the proportionality into an equation, if we want a formula, so Coulomb said, let's make a formula here. So he introduced a constant, right? So the Coulomb's law, the famous formula becomes F equal to some constant, capital K, I'm going to write here, Q1, Q2 by r squared. So remember, in gravitational force, we have a similar thing. Force is, the gravitational force is G m1 m2 by r squared. But there G was the universal gravitational constant, which is constant value throughout the entire universe. But here it is not the case with electrostatic force. This constant K depends on the material. So this is a very important point, that the constant K depends on the material or the medium between the two charges. Okay. So this K is dependent on the material. So the K over here depends on the material, or we say depends on the medium. Now in the next video, when we talk about permittivity, we'll explore more details here, how it depends on the medium. But for now, you can note that this value of K is maximum actually for vacuum, right? That means no medium. And that is a very important standard value which we should learn. So the value of K for vacuum, okay? So the value of K in the case of vacuum is 9 times 10 to the power 9. And can you guys tell me the unit here? Can we work out the units of K? It's very easy. Force is Newton, right? The unit is Newton. Distance is meter. So Newton meter square by Coulomb square, right? The SI unit of charge is Coulomb. So the SI units, look at the formula. Newton meter square per Coulomb square. Okay, very important value. You guys need to learn 9 times 10 to the power 9. Okay, so this is the famous Coulomb's law formula. right here, right? This is the famous Coulombs law formula, and that is the value of this constant K, which depends on the medium. Now, K depends on a permittivity factor. There's a 1 by 4 pi epsilon, but that we'll talk about in our next video on permittivity. Okay, so this is what Coulomb's law said. And again, we took this example for positive charges. If you have negative charges, two negative charges, again force will be in same direction. But if you have a positive and negative, again Coulomb's law works. This time the forces are once again along the line, but they are towards each other because it's an attractive force. Okay, so that was Coulomb's law for you. K times Q1, Q2 by R square, and they've said the charges are in vacuum. So we can use this standard value of K. So many times it will not be given in the question. You're supposed to know this value, 9 times 10 to the power 9 Newton meter square per Coulomb square. So see, these are all in SI units. So come on guys, can you calculate this for me? What will be the electrostatic force? Simple, we are going to write the Coulomb's law formula. Force equals K times Q1 Q2 by R square. K is 9 times 10 to the power 9 in SI units. Now Q1 is 5 microcoulomb, so micro means 10 to the power minus 6. Okay, so let's put that in here. 5 times 10 to the power minus 6, and then we have a 2 times 10 to the power minus 6. So those are our two charges, and the distance you can see is 10 centimeters, which is basically 0.1 meter, right? So, or 10 to the power minus 1 of a meter, right? It's 10 by 100, 1 by 10 by 100, 1/10 of a meter. So that we are going to put here, but it is 10 to the power minus 1 square. You guys can see that, right? It's 0.1 meter, which is 10 to the power minus 1, and don't forget the square over there. So now go ahead and calculate the value, simple. So take all the numbers together and all the 10 powers separately. So we have 9 times 5 2s are 10, so there's a 10 there, times 10 to the power 9, and there's minus 6, okay? So those are the two minus 6 over there, and then a 10 to the power minus 2. Now this is in the denominator, so it will become 10 to the power plus 2. So basically we are getting a 9 times, so we have a 10 to the power, this is 10 to the power 1 plus, this will give us how much? 9 minus 12, that's minus 3, and the plus 2 goes on top, right? So you can see that will all cancel off, 3 minus 3. So basically the final force that we are getting is 9, and what is the SI unit of force? You guys know, it is Newton. So just write that down over here. 9 Newton is the answer. Simple, so just apply Coulomb's law formula, and we have used this value 9 times 10 to the power 9 because it was in vacuum. If it was a different material, they'll give us the value of K or permittivity, which we talk about in the next video, and this is how you can calculate the Coulomb's law force easily. Again, what will be the direction here of the forces? You have a positive charge and a negative charge. So clearly the force is going to be attractive, right? So unlike charges, they attract each other. So both will be equal in magnitude, but opposite in direction, and they are an attractive force, as you can see in the diagram here. Now that you know the formula of how to calculate electrostatic force from Coulomb's law, let's talk about some important characteristics of the electrostatic force. So point number 1, we said that electrostatic force can be attractive or repulsive. So you guys remember that the force is attractive when there are unlike charges, positive and negative. But if there are like charges, as we discussed, the force is repulsive, right? They repel each other. And as we have discussed, the force acts along the line joining the two charges. So remember, when we talked about Coulomb's law, the force has to be along this line, not in any random direction. So this is a very important point, which is giving us the direction of the force. And this important point, you guys remember that the Coulomb's law is telling us it obeys, these electrostatic force obey Newton's third law, which means the two forces are equal in magnitude but opposite in direction, right? Because we know always forces occur in pairs, and so Newton's third law is also obeyed for electrostatic forces here. It is valid, this is a very important point, Coulomb's law. So Coulomb's law, we said, is valid only for point charges. So this point is basically for Coulomb's law. And note the spelling, guys, carefully. C-O-L-O-U-M-B, right? So Coulomb's law. That's valid only for point charges, which means the charge is tiny in size. Okay, so these are like tiny in size. When you're considering them, then you can use Coulomb's law force. Or that basically means that if I take a large ball here, right, some sphere, or let's say a cuboid or cube, and let's say it's a charged body, can I apply Coulomb's law? No, because then the charge is distributed across the entire body and it is no longer a point charge. Well, you can use Coulomb's law, let's say if you have two spheres, but they are separated very far away, right, at a very large distance, then we can assume that when the distance is very large, they seem to be like point charges for us, right? So the definition or point charge basically depends on the context, right? Either the distance is very large or they're really tiny in size. Force depends on the medium. So this is unlike gravitational force, right, which does not depend on the medium. Electrostatic force definitely depends on the medium, and that is why in the formula, remember, there is a K. So in Coulomb's law formula, F equals K times Q1 Q2 by R square. This K guy is actually dependent on the medium, and then in the next video we'll talk about how it depends on the permittivity of the medium. There's a formula 1 by 4 pi epsilon. I will not look at that detail over here, but this is basically the permittivity factor or the effect of the material on the force. The other important point is it is independent. The electrostatic force is independent of the presence of other charges. So what does this mean? That if we bring in a third charge over here, is it going to affect this force F12 and F21? No. There will be some other forces, so there will be an F13, there will be a F23 and all, but this force will not be affected. So that is what this point means, that if you introduce another charge, it does not affect the original forces between the two charges, let's say 1 and 2 here. And as we discussed, the force follows the inverse square law. So this is just like gravitation force, where you have the force is inversely proportional to the square of the distance. So there you can see from the formula, which means that if you double the distance, how will the force be affected? That's right, it's going to become 1/4. If you double the distance, the force becomes 1/4. If you triple the distance, the force becomes 1/9. If you half the distance, the force becomes 1/2 square, so it will become 4 times, right? So because there's an inverse over here, so you have to take a half square and then reverse it, right? So you guys get the point here, that it is inversely proportional to not the distance, the square of the distance, which is why we call it the inverse square law. So these are all the important characteristics of the electrostatic force, the force between two charges, or as we were discussing for Coulomb's law, two point charges. We have learned about Coulomb's law and Coulomb's law formula. Now let's look at Coulomb's law in vector form. So how does the formula look like in vector form? Let's take a look. So once again, we are going to consider that we have two charges and we'll take the two charges to be positive. Now, since the two charges are positive, they will repel each other with a force along the line joining these two centers, right? So these are the two forces. So I can say this is the force on charge 2 due to 1, F21, and this is force on charge 1 due to 2, F12. Now, Coulomb's law formula, we know that the magnitude of this force, right? So the force that we are talking about, the magnitude of the force is K Q1Q2 by R square. But remember that electrostatic force is a vector quantity. It has both magnitude and direction. So what we've learned till now is actually only the magnitude formula. What about the direction? Now you'll say the direction is along the line joining the centers, so that's also right. But I want to express it in terms of a vector form, right? So how do I give this direction? Okay, so for that, remember, whenever we have to give a direction, we take use of a unit vector. You guys remember? So can I say that the force, so let's say I'm talking about the force 1, 2. So can I say the vector force 1, 2 is the magnitude of the force times a unit vector? Now this unit vector A should be in this direction, right? In the direction of this force. So we have to say the unit vector A cap or A hat should be along this direction. Now how do I characterize that unit vector? So what we are going to do is, we are going to take some arbitrary point, like we'll take some origin over here. So let's say I take some origin right here, O, and I say that Q1 is located at at vector R1. So the position vector, so where is this charge Q1 located? It is located at R1, vector R1. And Q2, the position of Q2 can be described as by vector R2. And again, these are reference to a certain origin, right, that you have taken. Now, what is this R? This R is the distance separating the two. Okay. So here, when we talk about R, again, we use it in terms of magnitude. But can you guys tell me what is the connection between this R, R1 and R2? Okay. Or if I want to describe the the direction along this direction. So if I want to describe the direction along this direction, which is the direction of the force F12, what is it going to be? So remember, we can use our vector addition or vector, there's nothing called vector subtraction, vector addition, right? So we can say that if I want to describe this position vector, okay, so which means from Q2 to Q1, can I say this position vector, if I denote it as the vector R, guys, can I say R in this direction will be equal to R1 minus R2? Do you guys agree? The final position minus the initial position. Take a look. Will you agree with that? Or, you can also do, to get to R1, how do we get to R1? R1 is nothing but R2 plus R. You can go this way as well, right? The law of addition, the triangle law of addition. So you can do R2 plus R will give you R1, or I can directly say that R along this direction is the final position R1 minus R2. Take a look. Do you guys agree? R is nothing but R1 vector minus R2 vector. And which R I'm talking about? In the direction of F12. Clear? So look at this carefully. This R that we are talking about is nothing but R1. Let me write it here. This direction, along this direction, is nothing but R1 minus R2. So this is, at least I've described the direction over here, right? That means the vector along this direction. But remember, to put it into this formula, I need a unit vector. Unit vector means of magnitude 1, right? Having unit magnitude. But this one, no guarantee that this is unit magnitude. So how do I convert it into a unit magnitude vector? So we can say that our A cap will be R1 minus R2, so that direction, divided by the magnitude of this. If you want a unit vector in this direction, what do? You take that vector and divide it by the magnitude. As simple as that. So now I can substitute that and I'm going to get Coulomb's law in vector form. Do you guys agree? So everyone has got the logic here, right? That this direction, this vector is basically R1 minus R2. Okay, this is what this vector is. And I want a unit vector in this direction. So it's going to be R1 minus R2 by the magnitude, right? This is R1 vector, this is R2 vector. This vector is R1 minus R2. Okay, so there's my unit vector. Now all I have to do is I just have to substitute it over there. So therefore, what will I get? So I'm going to erase this. And therefore, what do I get? That F12 is the magnitude of the force, which we can copy down from here, K Q1Q2, right? So let's copy that down here. So we can say F12 is K times Q1 Q2 by R square multiplied by this. This is my unit vector along this direction. Okay. So multiplied by R1 vector minus R2 vector divided by the magnitude of R1 minus R2. But this formula is looking a little confusing because there's an R over there, then there is R1 minus R2. And remember, this R is not the vector, it is just the magnitude of the distance. So really this term is this. Do you guys agree? It's just the magnitude of the distance, not any direction over there. And will you also agree that this magnitude of R is same as this R1 minus R2, because this is the entire vector. So R vector and this vector are the same thing, right? So both these magnitudes are same. So either I can write this way, or I can put a cube over here when we multiply these. So what we can say, therefore, F12 is working out to be K, the constant K, Q1, Q2, okay, and then you have the R1 minus R2 vector. So this thing divided by, we'll get R1 minus R2 vector whole cube, the magnitude of that. Why do I get a cube term? Because of multiplying this, right? There's a square here and there's to the power 1. So this is the final, we can say vector form of Coulomb's law. The force on 1 due to 2 can be expressed like this, and this is in vector form. And don't think we have changed the law from inverse square law to inverse cube law. It's basically because you are multiplying with R1 minus R2. Clear? Now, guys, can you give me the expression of F21? So I've given you the expression of F12. Can you tell me what will be the expression of F21? It's simple. So again, we'll write the same thing, K. So the constant K, Q1, Q2. This time, the force will be in this direction. So I need a vector in this direction, this vector. So this time I'm going to do R2 minus R1. Do you guys agree? If I want this vector, this is my final position, R2, right? That's the position vector of it, minus R1. So I'm just going to switch. I'm going to say that this is going to be therefore R2 minus R1. And this one doesn't matter, but just to make it look consistent, we can say magnitude of R2 minus R1 whole cube. There you go. So we have got both the expressions for the two forces F12, F21 in vector form. See, these are all vectors. So we have characterized both the magnitude, we have captured both the magnitude and the direction. Clear? So that was the trick. We used R1 minus R2 this way and R2 minus R1 that way. And basically we use the concept of the unit vector, right? The vector divided by its magnitude. And there you go, Coulomb's law in vector form. So simple. Let's compare gravitational forces, which is the forces between two masses, and electrostatic forces, the forces between two charges, and you'll see there are some interesting similarities and differences. So to compare first, let's quickly write down the formula. So what is the formula of gravitational force between two masses? Remember, gravitational force I'm going to write as Fg is G m1 m2 by r square. And the electrostatic force between two charges, I'm going to write it as Fe, the electrostatic force, is K Q1Q2 by r square. So these are the formulas, right? Now can you tell me what is the similarities between the gravitational force and electrostatic force? So if you look at the formulas carefully, you can see that there is this inverse square, right, of the distance. So you have inversely proportional to r square. So we can say that both of them follow the inverse square law. Both forces are following inverse square law. If you look at the formulas, again, there is a similarity, m1, m2, product of masses, product of charges, q1, q2. So let's write that down. They are basically following this concept of product. They depend on product of masses or charges. What about their direction? So remember we talked about the force acts along the line joining the two masses and also the two charges, right? So the same concept that the force is along line joining the masses and charges, right? So this you can complete. You guys got that point. And another very important thing, both gravitational force and electrostatic force are conservative forces. What is the meaning of conservative force? The work done does not depend on the path taken. So it doesn't matter if you move it like this, or like this, work done will be same. Or if you bring it back, what is the work done? That's right, it's going to be 0. So both the forces are conservative forces. So these are the important similarities between gravitational and electrostatic forces. What are the differences, guys? So if you compare the two forces, we know that gravitational force is always attractive. Masses, they always attract each other. But electrostatic forces, we talked about that electrostatic force can be attractive when you have unlike charges or repulsive when you have like charges. So this is an important difference. Gravitational force is always attractive. So gravitational force always attractive. But the electrostatic force, it can be attractive or repulsive. Attract or repel. Okay. What is the other important difference? Gravitational force, right? It does not depend on the medium. right? So if you have, is it vacuum or there's some material in between, because this G is a universal gravitational constant. So this is an important point. Gravitational force, it is independent of the medium separating the masses. But electrostatic force, this constant K absolutely is not constant throughout the universe. It depends on the material, the medium between the two charges. That means whether there is, whether it's vacuum, is there some liquid, oil, water, glass, right? So electrostatic force, it depends on the material, depends on material or medium between the charges. Clear? So here we have summarized the important similarities and differences between gravitational force and electrostatic force. Now if I ask you which force is stronger, the gravitational force or electrostatic force, what do you guys think? Well, let's take a simple example and do the competition between these two forces. So let's say we have two electrons. Okay, so electrons, you guys know, are negatively charged. So we have two electrons and let's say they are separated by a distance of 1 meter. We are going to look at what is the gravitational force between the two electrons and the electrostatic force and which one is stronger. So let's try it out. Guys, do you know what is the mass of an electron? So you can check it up. You should know this value. Mass of an electron is 9.1 times 10 to the power minus 31 kg. See, I'm taking all SI units to make it easy. And you know the charge of the electron is minus 1.6 times 10 to the power minus 19 Coulomb. Okay, so that's the charge of the electron in SI units. And they're separated by a distance of 1 meter. So let's look at what is the gravitational force between these two electrons. These two electrons, gravitational force, they're going to attract each other, but the electrostatic force will repel. So finally, we have to see who wins, right? Will the two electrons repel each other or will they attract each other? Okay, or maybe they cancel. Let's take a look. Okay, so gravitational force, we know the formula G m1 m2 by r square. Guys, let's substitute the value. You guys remember the value of gravitational constant is 6.67 times 10 to the power minus 11. The two masses are 9.1 times 10 to the power minus 31 whole square divided by the distance is 1 meter. So the denominator is easy, 1 square. So let's go ahead and write this out. So we'll bring all the numbers together. 6.67 times 9.1 whole square times 10 to the power, we have a minus 11 and then we have a minus 62 here, right? So how much does that give us? Minus 11 and minus 62. So that will give me minus 73. So there's a 10 to the power minus 73. So this is again in Newton, the gravitational force between two electrons. So you can see it's very tiny, right? 10 to the power minus 73. Now let's compare this to the electrostatic force. The electrostatic force of repulsion between the two electrons. So electrostatic force, we know we calculate from Coulombs law, K Q1Q2 by r square. Again, we're going to assume that this is vacuum, so the value of K is 9 times 10 to the power 9. The two charges are 1.6 times 10 to the power minus 19 square. And one important thing, see, I did not substitute the negative here, right? Because in Coulombs law formula, we do not bother whether it is positive or negative, only the magnitude matters, right? So the sign is not important in Coulombs law. You just, the sign of the charges determine the direction of force, okay? So that's an important point. No need to put in the sign over there and divided by, once again, 1 square. So here what do we get? We get a 9 times 1.6 square times 10 to the power 9, and this is 19 times 2 is 38, so we are getting a minus 38 here, divided by 1, okay? So if you guys do this, what does this value end up to? 9 minus 38, so 9 minus 39 would be minus 30, so I think that's minus 29 here, 10 to the power minus 29. And the unit is Newton, so this is the electrostatic force. So clearly, guys, who's the winner? It is electrostatic force, right? because it's only a 10 to the power minus 29. Here you have a 10 to the power minus 73, and of course there are some numbers in front, right? So to get a better feel, we can simply take a ratio, right? So we can, you guys can take a ratio of Fe by Fg. So calculate the ratio of these two numbers, and you'll see that approximately it is 10 to the power 42. 10 to the power 42. The ratio of the electrostatic force to the gravitational force. So finally, will there be repulsion or attraction? The electrostatic force is 10 to the power 42. So 1 and 42, 0 times stronger than the gravitational force. So clearly, guys, these two electrons are going to, so electrons will repel each other. So electrostatic force is much stronger. So we can say this guy is the winner. Electrostatic is much stronger than gravitational force. In fact, we say gravitational force is one of the weakest forces in nature. Gravitational force comes into account when one of the masses at least is large, right? Like the force between me and the earth is reasonable, right? My weight. But the force between me and the camera, it's very tiny. Otherwise, the camera would have fallen down here, right? So if I was pulling the camera that hard, it would have just fallen down and the video would have stopped here. So gravitational force very weak compared to electrostatic force, which is the clear winner here. Here's an interesting question for you. The question says a charge is divided into two parts such that the force between the two charges is maximum. Find this charge on each part. So let's say you have some charge Q. It could be 5 Coulomb, 10 Coulomb, 20 Coulomb, whatever. And you divide it into two parts. Okay. So basically the question is telling us that you are dividing your full charge Q into two charges, Q1 and Q2. And let's say the full charge is capital Q. So this charge will, let's say it is X. So how much will this charge be? It's going to be Q minus X. Make sense, right? So the total charge is divided like this, X and Q minus X. And let's say they are separated by some distance R. Okay. That distance is not given because this distance is fixed. We are just caring of how, we just care about how do you divide the two charges. What is our goal? So that the electrostatic force between the two charges is maximum. So once again, you can consider they are positive charges. So they are repelling each other. Okay. So what will be the electrostatic force here? So from Coulomb's law, F we know is K Q1Q2 by R square. So that will be the constant K. Q1 is X. Q2 is the total charge minus X, Q minus X divided by R square. But how do we find the value of X, right? So if I can get X, the value of X, so that this force is maximum, right? So we need to find X. So the goal here is find X so that force is maximum. Clear? The goal is clear. And this is where we take the help of mathematics or what we know from calculus that see, you can see this force is a function of X. So for maxima or minima, what do we do? That's right, df by dx should be equal to 0. The slope should be equal to 0. You're at the maxima or the minima, right? So we say for maximum, so for maxima or maximum force, we can say df by dx is equal to 0. That means if you differentiate this force expression with respect to x, it's going to be equal to 0. So do the differentiation, solve, and get the value of x, right? That's what you need to do here. So we need to do a ddx of this force expression. So we just copy down this expression here, kx q minus x by r square equal to 0. Now guys, get all the constants outside because constants we know come out of the differentiation. So we can see here that k is a constant, and the distance is a constant. So we are going to bring them out here. So basically we have k by r square ddx of, we are left with x times q minus x, okay, equal to 0. Now the constants will basically go on the other side and become 0. So we care about this differentiation. So basically what you're doing is the ddx of qx minus x square equal to 0. ddx of qx is nothing but q, right? ddx of x is 1 minus 2x equal to 0. So if you solve this, what do you get? X is equal to q by 2. What does that mean? that the one charge is q by 2, the other charge will be q minus q by 2, which is q by 2. So basically, to get the maximum force, you need to divide your charge into two equal parts. So if you have 10 coulomb of charge, 5 coulomb. If you have 5 coulomb of charge, 2.5 coulomb. So that is what this interesting question is telling us, that the charge will be equally divided, right? So that the force is maximum. And again, you can see we use the concept of calculus to get to the answer here. So Coulomb's law is great in helping us calculate the electrostatic force between two charges, but it has some limitations. So the important first limitation we have already discussed, that it is valid only for point charges, right? So it is valid only for point charges, which means the charge needs to be tiny in dimension, right? The size of the charge should be really, really tiny, or if it is reasonable, like a sphere or some ball or cuboid or whatever, some large size body, then the distance has to be very large so that we can ignore the dimension of the body. Then you can apply Coulomb's law. But if the charge is, let's say, distributed on a ball, right, or a cuboid or some large object, right, and you want to look at the force near it, then we cannot apply Coulomb's law. Then we are going to do something where we will use the charge distribution, right? Because there the charge is distributed along the mass, so Coulomb's law is not applicable there. The second limitation of Coulomb's law is that both the charges that you're considering, they cannot be in motion. So basically it is telling us that either, so both charges are at rest, so both charges at rest, then Coulomb's law works, or one charge is at rest and the other is in motion. So one charge can be at rest, the other in motion, but both charges, if they are moving, then you cannot apply Coulomb's law. So these are the important limitations of Coulomb's law. Till now, we have been talking about two charges, but what if you have three charges? So if you have a situation like this, where let's say Q1 is a positive charge and we have two charges, Q2 and Q3, which are both negative. Now, let's say I want to find what is the force on Q1 due to these two charges. So how do I calculate it? Can I apply Coulomb's law? The answer is yes, because remember Coulomb's law said that the force you can calculate between two charges will be independent of the third charge. So basically what this means is that when you are looking at the force on Q1, on charge 1, due to 2, you can ignore 3. Okay, so note this point, you can ignore 3. So basically what we are going to look at is, we're just going to focus on Q1 and Q2, and you can see that both one charge is positive, one is negative, so that two charges will attract each other. So let's say I'm interested in the force on 1 due to 2, so I can mark it like this, F12. So this is going to be F12, and how do I calculate it? I calculate the value using Coulomb's law. F12 is going to be K Q1Q2 divided by the distance, let me call it R12, or let's call it, let's say a distance A here, so A square. So let's say the distance of separation is A between these two charges. Clear? So that's the magnitude and this is the direction. Now let's say you want to know the force between these two charges. So this is positive, this is negative. Again, the direction of the force will be along the line joining the center of the two charges. It is an attractive force because you have positive, negative. So the force is going to be in this direction, F13. And let's say the distance separating the two charges is B. So what will be the magnitude of F13? Again, F13, this force is independent of Q2. That's what Coulomb's law tells us, right? It is independent of the other charges. So F13, we can calculate again using Coulomb's law formula K Q1Q3 divided by B squared. So there we've got that distance. But the question is that if I want to find the total force or the net force on 1 due to both these two charges, due to both of these charges, what do I do? So you can see that Q1 is experiencing two forces. Now if we want to find the net force, what do we do? That's right, we just simply take a vector sum we just have to take a vector sum of these two forces, because remember these two forces are vectors. So your F1 and F2 vector, you just need to add these up. We need to take a vector sum, and you can guess it's going to be somewhere along this direction. So let's say the vector sum is in this direction. So I'm going to call it force 1, force on 1 due to both these charges is going to be F12 plus F13. As simple as that. So what we've done is we have taken a vector sum. So this is what we call as the principle of superposition of forces. Fancy name, but basically what you're doing, you're just taking a vector sum of the two individual forces, right? To find the net force, it's going to be F12 plus F13. Let's say this charge was positive, then the force would have been this way, right? And the vector sum would have been this way, okay? So that depends, okay? And so because forces are vectors, so remember we are not just taking a sum of the magnitudes, you don't just add these up, you take a vector sum here. So this is an important concept to keep in mind when you are given multiple charges. So let's look at some questions where there is not just two charges, but more than two charges. Here I have a question for you where this time there are four charges. And the question says, find the net force on the charge placed at A. So you can see that we have a square here of side 1 meter, and you have the identical charges on the four vertices of the square. We need to find the net force on this charge placed at A. So how do you do it? So here again we are going to use the concept, the principle of superposition of forces, because we have multiple charges, and the key concept is that you have to take a vector sum of all the individual forces. Okay, so here we are going to look at the force. So since we are interested in the force on charge A, let's look at the force due to charge B. So both are positive. So therefore you guys know that this force is going to be repulsive in nature. So the force due to B, which I'm going to mark as FB, is going to be in this direction. Similarly, the force due to D is going to be in this direction. Yes, repulsive force. And the force due to C is going to be in this direction along the line joining the two charges. So FC is going to be something like this. The question says find the net force on A. So we can say the net force is going to be equal to the vector sum of FB plus FC, the force due to B, the force due to C, and the force due to D. Do you guys agree? Now we can individually apply Coulomb's law for each of the forces. So what will be the magnitude of the force due to B? FB is going to be K Q1 Q2 by R square. So K times both the charges are same. So it's K Q1 Q2 by R square. So which is basically going to be K Q square divided by the distance is 1 square, right? So you can see this is going to be K Q square by 1 square, which is basically 1. Okay. Similarly, what will be the force due to D? If you look at D, so force due to D will also be the same. Force due to D will be KQ square, right? Since the distance is same, so I'm going to remove that one term. So KQ square. Now, what about the force due to C? So what is the distance here? So see, this is 1 meter, this is 1 meter, and a square, we know that this is a 90-degree angle. So this is the hypotenuse. You have a right angle triangle hypotenuse. How do you calculate the hypotenuse? A square plus square root of 1 square plus 1 square. So this is basically going to be root 2 meters. Yes. So the force due to the charge at C is going to be K Q1 Q2, which is KQ square, divided by the distance will be root 2 square. So basically we get KQ square divided by 2. That's what we have here. That is the force due to C. Now, how do we do the vector sum? So this is the important thing. How will you do the vector sum here? Because you can see we have three forces, right? So this is the point A. We have FB along this direction. We have FD along this direction. And we have a FC along this direction. So FB and FD are making an angle of 90 degree. Okay. So how do I do a vector sum of FB and FD? So remember in vector addition, what do? If you want to find the magnitude, it's going to be square root of a square plus b square plus 2ab cos theta, right? The angle between them. So if I want to find the vector sum, the magnitude of, if you want to do fb plus fd, then the magnitude of that will be, so magnitude of this force is going to be square root of fb square plus fd square plus 2fb fd cos theta. Now what is the angle? Theta you can see is 90 degree. So cos of 90 is 0. So this term disappears. So this term is gone. So basically what are we getting? Square root of fb square plus fd square, which is, and both these forces are identical, fb and fd. So basically I am getting square root of 2 times kq square and square of that, right? So when you take a square root, so basically what you're going to get? A root 2 kq square. So you guys can plug it in and check that. This is only the resultant due to fb and d, so I can call it fbd. Now what will be its direction? Because both forces are equal in magnitude, right? You can calculate the angle also, tan theta, but you will see basically finally it will come to be 45 degree. So they're going to act along, exactly along this line, which is the line of the line of action of the force C. So do you guys see here that the resultant of FB and FD will be along this line, right? So your FBD will be along this line. So the net force, we can simply add it up. We know its direction is going to be this way. So the final net force is going to be this value, the magnitude, root 2 kq square plus the force due to C, which is kq square by 2. So if you take kq square as common, we are getting root 2 plus half, and that's the final answer. Okay, and we can put over there Newton, right, or whatever units. So this is the net force. And if they ask you the direction, what is the direction? It is along this diagonal, the diagonal of the square, and it is away from this, right, away from C, because these are all repulsive forces. So if they ask about the direction of the net force, we can say is along the diagonal, along CA, right, from C to A. So the direction is also known. So this is how you have to do these questions. You basically need to look at the diagram carefully. You take a vector sum, principle of superposition of forces, you calculate, and you will simply get the answer. Okay. So again, this is how you approach these questions. Take the individual forces, do a sum, but remember to do a vector sum. So that part you have to do carefully. And here we use the vector formula to find the magnitude. Come on, let's try another interesting question. This time we have the 3 charges on the vertices of a triangle. And I would encourage you to pause the video, try the question yourself. Then you look at the solution here. So what has been asked here? Find the net force on the negative charge which is placed at the center of this triangle. So there's a minus q here and there are 3 plus q's, and you can see it is an equilateral triangle because all the sides are equal. So how do you approach it? Once again, we're going to apply Coulomb's law and the principle of superposition of forces, right? So we have to take a vector sum here. So let's consider all the 3 forces. So let's mark this triangle. Let's say this is this vertex is A, B, C. Let's look at the forces. So we must draw the line joining the 2 charges. So what will this force be due to A on B? Or let me just join the line of all these 3 charges. So we want the force on the negative charge, right, due to A. So they are unlike charges, so there will be attractive force. So the force on minus Q is going to be this way, towards A. Similarly, the force on this negative charge due to B is going to be this way, FB, and we will have another force here, FC. Now what will be the net force on minus Q? We will again apply that simple concept that the net force is going to be the vector sum of the 3 forces, Fa plus Fb plus Fc. But the problem here is that the 3 forces are in 3 different directions. So how do we do a vector sum here? We cannot simply add it up here, right? So we will again use the concept of vectors where we break it down into their x and y components. Remember, so that is the strategy, that you need to break down these forces into their horizontal and vertical components. So let's go ahead and do that. So for that, let me go ahead and draw these axes over here. So let's say this is the x-axis, the x or horizontal components this way and vertical components this way. Okay. So you can see FA is clearly along the vertical component. It is along this positive y-axis, right? And this is our x-axis. So FA is not a problem, but these guys we need to break down into their horizontal and vertical components. For that, we need to know this angle. So if this is FB making an angle, let's say theta with the horizontal, I need to know how much is this angle. So how much will it be? So here, if you see carefully, guys, this is an equilateral triangle. So if you look at this triangle, this is an equilateral triangle, and each angle is 60 degree. And we know that since this is in the center, this line joining this is basically going to bisect that angle. So this angle here will be 30 degrees, and this angle will also be 30 because the total is 60. Now, if this angle is 30, can you see that this is the base and this x-axis, they are parallel to each other. So we will get alternate angles over here. If this is 30, do you guys agree? This angle will be 30. And the same case with FC. This angle is also 30 degree with the base, with the horizontal, okay, the x-axis. So now we can easily break the components FB and FC. So FB is right up to here. So we can split down into the horizontal and vertical component. So FB will be, so this side will be how much? This is the base. So this is going to be FB cos theta or FB cos 30. So this side, do you guys agree? This is going to be FB cos 30. And this way, it's going to be the sine component, FB sine 30. And same story for FC. FC, this side is going to be FC cos 30. And this side is going to add up here and be FC sine 30. And for A, we just have it along the y-axis. So can you see in this diagram, we have broken down all our these two forces, and this one was easy, along their x and y directions. So now we have to do vector sum along the individual directions along the x and y. So let's go ahead and do that. So we are going to find along the x direction. So along x-axis, what is the case? The F net along the x-axis. So we can say F net along the x, or we can call it Fx, right? Fx net. That's going to be what? We just have to look at FB and these horizontal forces, FB cos 30, FC cos 30, they are in opposite directions. Okay, so they are going to be subtracted. So we are going to do FB cos 30 minus FC cos 30. Now guys, if you look carefully, this is a full symmetric case. The charges are identical. All these distances from the center will be identical. So will you guys agree with me that the magnitude of all these forces, FA, FB and FC, are going to be equal, right? K Q square by whatever, let's say this distance is R. So does everyone agree that FA will equal to FB is equal to FC, and that is equal to some K Q square by whatever the distance here R? So all the forces are equal. So that means all of these two terms are identical. So the net force will be basically KQ square by R square, and the cos 30 will cancel, right, times 0. So net force along the x-axis, basically these two forces are cancelling each other. So net force along the x-axis is 0. Simple. What about the net force along the y-axis? So along the y-axis, the Fy net is going to be equal to Fa. So this is along the positive y-axis, Fa minus these two components, Fb sine 30 and Fc sine 30, right, which are vertically downwards. So minus Fb sine 30 minus Fc sine 30. Now all these forces are same as we discussed, right? So they are all same. So we can take the force common, KQ square by R square, and we'll get 1 minus sine 30 minus sine 30. Guys, what is sine 30? Sine 30 is half. So basically we are getting 1 minus half, and guys, there also we are getting 1 minus 1, which is 0. So can you see that the net force along the x-axis and y-axis both are 0? Therefore, we don't have to do any vector sum. We know that the total force is going to be 0. Therefore, we can say F net, the net force on the negative charge is 0, and that is our final answer. So this is the trick. If you get these complicated forces which are in random directions, just break it down into x and y components. So make sure you draw a diagram neatly, and there you can calculate along the x and y axis, and that is our answer of the total net force on this negative charge is 0. Here's an interesting question for you to try. The question says, at what position should a charge be kept so that it does not experience any force? Okay, so let's say you have been given these two charges. One is plus 9q, the other one is plus q, and they're separated by a distance of 2 meters. I need to find, so let's say I have a test charge, and again, we are positive people, so we're going to take it as plus q. I need to find where should I place such a charge so that it experiences zero net force. So now if you consider it along the line, so the question didn't say that, but let's say we are considering along the line of the two charges. So if I place the charge, so we are interested in placing the charge along the line of the two charges. Now guys, let's say you place your test charge over here. So your plus q is over here. Can it experience zero net force? So this 9q is going to repel it away. Even this plus q is going to repel it away. So both the electrostatic forces will be in that direction. So they can never cancel. So this option is out. Okay. What about if you place the charge here? Again, the same situation. Electrostatic force repulsive this way. That charge is also positive. Like charges repel each other. So another force this way. Again, we can get no, the net force can never be zero. So these two options are out. Okay. We can't place it here. We must place the charge, or let's try it, between these two charges. Now, should we place it exactly at the center? Probably not, because this is 9q, this is q. So let's say I don't know the location. Okay. But intuitively, you're getting a feel that it's probably going to be closer to the weaker charge. So let's say we place the plus q here. Now, I don't know this distance, so I'm going to say this distance is x. And the remaining distance will be 2 minus x. It was given total distance is 2 meters. So x, and we have 2 minus x. So you need to find this position where the two forces due to these cancel. Now, is that possible here? Because you can see that this charge will have a repulsive force this way. So there will be an F1. So, or let's say this is 1 and 2. So there's an F2 due to charge 2 this way. And there is a F1, a repulsive force due to charge 1 that way. And we want both these forces to cancel. That is the question. You need to find this position x where the two forces cancel out. The question is clear? So now guys, I want you to try this question. This is your homework question. Go ahead and try it out, and do let me know your answers by putting it in the comments below. So come on, all of you, use the concepts we've learned, try out this question and tell me at what position the net force on this test charge is going to be zero. You could have also taken a negative charge, doesn't matter. But we've taken a positive charge here. So go ahead and find the distance, and do let me know your answers in the comments below. I look forward to reading your answers, and I promise to reply to them. Let's summarize what we have learned in this video. So remember, the main concept we have learned is Coulomb's law, which is describes the force. It gives us the formula for force between two charges. So the electrostatic force, right? So let's say we have two positive charges. We've taken that example. Two positive charges separated by a distance r. Coulomb's law told us that the force will act along the line joining the two charges. So let's say you have a force here F12, and similarly you will have a force here F21. Can you see that these forces are repulsive forces? These are repulsive forces because they are like charges. If you had a positive negative, then the forces will be attractive forces. And these two charges are separated by a distance r. So remember, these two forces are electrostatic forces which are equal in magnitude but opposite in direction. So they are following Newton's third law. And Coulomb's law told us that the force, remember, it is proportional to the product of the two charges Q1, Q2, right? And inversely proportional to the square of the distance between the two charges. So finally, we got this formula for Coulomb's law, F equals K Q1 Q2 by R square. Where what is this K? This constant K depends on the material, the medium, whether there's vacuum, water, right, or some other liquid, oil or glass. So K is dependent on the material, the medium between the two charges. So depends on the medium. And remember, we said Coulomb's law is valid only for point charges. So these charges are very small in dimension, like tiny charges, right? They could have a certain charge, but they're tiny in dimension. So that is when you can confidently use this formula for the electrostatic force. So many times you'll see it's written Fe. This is the electrostatic force, and this is the formula K Q1Q2 by R square. And we saw it is much, much stronger than the gravitational force. Now, how this K, how does it change with the medium? For what medium is it maximum? There's a term called permittivity. So we'll be talking about in the next video that how K is equal to 1 by 4 pi epsilon, and we use epsilon not for vacuum. So this we'll be discussing all these concepts in the next video on permittivity. And remember Coulomb's law, the force is independent of the other charges. So if you have multiple charges, then we can take a vector sum and we can apply the principle of superposition of forces. So that is a quick recap of what we did in this video on Coulomb's law and electrostatic force. Friends, I hope you enjoyed this video and the concepts are crystal clear to you now. Do check out the full courses on our website manochaacademy.com and our Android app Manocha Academy. All the links are given below. We have courses on physics, chemistry, biology, maths, coding and artificial intelligence. In these courses, you're going to get live classes, concept videos, quizzes, questions, mock test and revision notes. So guys, what are you waiting for? Do check out the links given below and please do share it with your friends. And if you haven't subscribed to our YouTube channel, come on, smash that subscribe button right now and click on the notification bell so that you don't miss out on any of our videos. And do hit the like button and share this video with your friends. So guys, stay connected with Manocha Academy and enjoy your learning.